So in this video, what we're going to do is we're going to actually generate an inverse of a matrix using elementary matrices. And so it's really handy to be able to do this. The other thing that we're going to be doing is we're going to be generating an LU decomposition of a matrix. And in order to do that, we're going to show you how we're going to transform a trace of the row reduction of a set of elementary row matrices into the inverse of a matrix. So that's basically what we're going to be doing. We're going to be doing those three things. And hopefully by that point in time, you'll have a really clear sense of how it is that we do row reduction using elementary matrices and how they convert into inverses. So if you haven't done any work with elementary matrices, I would recommend that you either watch my video or you got to go in and do some work with elementary matrices in order to figure out what they are, look at how it is that we generate them, and how do we use them for row reduction. I put the link to the video, my video on that, inside of the comments here on YouTube. What I want you to do now is to recall that we had three kinds of elementary matrices. We had permutation matrices, multiplication matrices, and addition matrices. So let's start out talking about the inverses of each one of those kinds of matrices. Starting with permutation matrices, remember we had Pij, and that switched the ith and the jth row. Well, it turns out if we want to switch back those rows, which is what we're going to do when we take an inverse, Pij inverse is just going to equal Pij. So it is its own inverse, and it makes sense. If I went in and I switched rows 1 and 3, and I wanted to switch rows 1 and 3 back, how would I do that? Well, I would switch rows 1 and 3 again. I'd do the same thing. So for example, if we have P13, for example, and we know that that's going to be 1, not 1, but 0, 0, 1, 0, 1, 0, 1, 0, 0. Okay? We'll go in and we'll switch the first and third columns. So P13 inverse is just going to be the same thing. And it'll be 0, 0, 1, 0, 1, 0, 1, 0, 0. Go ahead and multiply the two of them together, and what you should get back, and what you will get back, is you'll actually get the identity matrix when you multiply P13 times P13. So the permutation matrices, they have pretty simple inverses. The inverses for multiplication matrices are also pretty simple. So if you remember, we have MIK, and that is that we're going to multiply the ith row by k. So what we're going to do in order to invert is we're actually going to have MIK inverse is going to be, we're going to multiply the ith row, but we're going to then instead multiply it by 1 over k, right? Because 1 over k times k is going to end up equaling 1. So that's going to take us back to that identity matrix, and that's exactly what we should have. So for example, if I take M2 negative 1/2, and we see that that's, as a 2 by 2, we'll make that 1, 0, 0, negative 1/2. Its inverse, M2 inverse of negative 1/2, is going to equal M2 of negative 2, and that'll be then 1, 0, 0, negative 2. Go ahead, do that multiplication. You're going to see that you actually get back the identity again. So what will we do? We'll take the inverse of k, right? It's multiplicative inverse, 1 over k, and we're going to place that into the row that we used for our original matrix. Okay, so no change there. Now finally, when we're working with addition matrices, it's a little bit different, and it may be slightly counterintuitive, but it will actually make a lot of sense if you think about it. So what we're going to do is we're actually going to say we have Aij and say Aijk. And so what we do is in Aj, we put k. And the rest ends up being the identity matrix. So for example, if I take A13, negative 2, that's going to end up equaling, we got 1s on the diagonal, and in A31 is going to equal negative 2, so A31 is down here, negative 2. So we have 0, 0, 0, 0, 0. Everything else becomes a 0. The inverse, it turns out, is just going to be A13, but it's going to have a positive 2 in it. All right? And so essentially what's going to end up happening is we're going to imagine that we're going to add 2 times row 1, okay, to row 3. To get where we got in the first place, we added negative 2 row 1 to row 3. So to like reverse that, we should add a positive of that, right? That'll actually reverse the process. So that means that A13 negative 2 inverse is just going to equal, it's going to look exactly the same. It's going to be 1, 0, 0, 0, 1, 0, 2, 0, 1. It'll look exactly the same, except instead of being a negative, it's going to be a positive. So let's actually look at that. Let's take those two matrices and we'll multiply them together, and you're going to see why. It's actually kind of cool when we multiply them. We got 1, 0, 0, 0, 1, 0, negative 2, 0, 1. And we could actually right multiply or left multiply. It doesn't really matter. We got 1, 0, 0, 0, 1, 0, 2, 0, 1. And when we go in and we multiply, here's what we're going to get. We got 1 and then 0 out along this row, so we're going to get 1 on the top. And that's going to be the case for the first row. The first row is going to give me 1, 0, 0. Second row, 0, 1, 0. So it's going to be 0, 1, 0. And remember, it's only the third row that's going to change. So I've got negative 2 times 0. Or excuse me, negative 2 times 1, that's negative 2, plus 0 plus 2, so that becomes a 0. Then I have negative 2 times 0, plus 0, plus 0, that ends up being 0. And then negative 2 times 0, plus 0, plus 1, and that's the 1. So what ends up happening, if you notice here, this negative 2 multiplies by this 1, and this 2 multiplies by this 1, and we add the two of them together. They add together in order to make a 0, and they 0 out. And we end up with our identity again. So when we want to find the inverse of Aij, Aijk inverse is simply going to be Aij, again, but negative k. So we'll take the negative of the scalar, and that'll end up giving us our inverse. Okay, so what we're going to do now is we're going to do an example, and we're going to change the trace of a row reduction into the inverse of a matrix. So a couple of things that we're going to have to recall is, one, is we're going to have to recall that if I take A times B inverse, that actually ends up being B inverse A inverse. So what we get here when we actually take the inverse of a product of two matrices is we're going to take the inverse of each additional one, okay? But then we're going to have to reverse its order. And this, of course, is only if, well, yeah, only if A and B are both invertible. Now, it's not only the case that we'll have AB inverse equal to B inverse A inverse, but also if I say, for example, I have A, we'll call this A1, A2, A3 inverse, that'll end up equaling, and actually, why don't we go to AN inverse? AN inverse, that ends up equaling AN inverse, AN minus 1 inverse, all the way down to A2 inverse, A1 inverse. So essentially, we'll go in and we'll multiply the inverses, but we do it in the opposite order, okay? And that's going to be important for when we actually draw this kind of trace. So let's say, for example, we take the matrix. So consider the matrix that we had was 2, 3, 5, 1. And when we went in and we decomposed that, right, into elementary matrices, when we row reduced it down to the identity, what we got was we got the matrix, we had A, our original matrix, so that's our A, and then we multiplied it first by M1 1/2, and then A12, negative 5, M2, negative 13 over 2, and then A21, 3/2. And so that was our decomposition. That gave us the identity, I2 by 2. What I'm going to do is I'm going to note that each one of these matrices, A21 up through M1, are invertible. In fact, A is also invertible. A is invertible because we row reduce it down to the identity. So consequently, it's got to be an invertible as well. But even so, we are going to actually end up getting ourselves this inverse utilizing these elementary matrices. So what I'm going to do is I'm going to actually take the inverse of each one of these, okay? So the inverse here of A21, 3, 2 times M2, negative 13 over 2, A12, negative 5, and M1, 1/2. And that's going to equal I. It turns out that this matrix right here too, that is going to be A inverse. How do we know it's A inverse? Because A inverse A, right, should equal the identity. In this case, I2 by 2. And that's in fact exactly what happened. So consequently, it's got to be the identity. That's the thing that has that quality. Well, what we're going to do now is we're going to go in here, we're going to take that inverse, and I'm going to multiply I2 by 2 by the inverse of those values. All right, so let's consider A equal to 2, 3, 5, 1. What we're going to do is we're going to utilize A here in order to find the inverse of A. All right, and then also we're going to utilize that inverse then to write A as a series of elementary matrices. Okay, as a series of elementary matrices. So what I'm going to do here is I'm actually going to write this and I'm going to say, okay, well, if you remember when we row reduced A, we got A and we multiplied on the left-hand side by 1/2. And then again by A12, negative 5. And M2, negative 13 over 2. And then A21, 3/2. That ended up giving me the identity. It gave me I2 by 2. Now, since I have I2 by 2, I2 by 2 is, in fact, yeah, right, that's the identity. What we want to notice is that I multiplied this whole thing by A and got the identity. What that means is that A inverse is this. So A inverse ends up equaling A21, 3/2, M2, negative 13 over 2, A12, negative 5, M1, 1/2. Great. And so we can in fact go in and we'll write the inverse as, you know, these elementary matrices. What about finding A? What is A going to be? Well, A actually equals A inverse inverse. And so what we're going to do is we're going to say, okay, well that means that that's A21, 3/2, M3, or M2, excuse me, negative 13 over 2, A12, negative 5, and 1, 1/2. Inverse. We're going to utilize this fact right here, right? Remember that the inverse of a product of matrices is just the product of the inverses in reverse order. So that means that A is going to equal M1 to the 1/2 inverse, A12 to the negative 5 inverse, M2 to the negative 13 over 2 inverse, A21 to the 3/2 inverse. And so, in fact, we can write A now. We're just going to use that information that we had about finding the inverses. So the inverse of M1, 1/2 is M12. The inverse of A12, negative 5 is actually A12, 5. M2, negative 13 over 2 is M2, negative 2 over 13. And A21, 3/2 is just going to be A21, negative 3/2. So that's what A is going to be. Right? We'll take the inverse of our elementary matrices, each one, and we're going to reverse their order. Okay? And that's essentially what you've got to do in order to find these. So A is going to equal, now I'm going to do each individual one, it's going to end up being 2, 0, 0, 1 times, and we'll have in A21, we're going to put a 5, so this is going to be 1, 0, 5, 1. 1, 0, 0, negative 2/13, and 1, negative 3/2, or excuse me, 1, yeah, 1, and we're going to put in 1, 2, we're going to have, that's going to be negative 3/2, 0, 1. And there that is. That's what A is. That's its decomposition into elementary matrices. Okay? So since A is invertible, and this is the only reason why this will work, we can write A as a set of elementary matrices. And that actually finishes that up. So there's A. A is our set of matrices, and A inverse, on the other hand, is just the original elementary matrices in the order in which we originally had them. Let's take a look at another example. So let's take a look at our second example here. So we have A equals 1, 0, negative 1, 1, negative 2, 1, 0, 1, 1. And when we went in and we did elementary row operations and changed those into elementary matrices, we got A311 times 1 times A32 times negative to the negative 1, M3 1/5, A232, P23, A12 negative 1 times A. And that'll equal I 3 by 3. We ended up having the identity. So A inverse, again, because multiplying on the left-hand side by A, all of these matrices gives you I 3 by 3. A inverse is just thus going to equal A311, A32 negative 1, M3 1/5, A232, P23, A12 negative 1. So A inverse is simply going to be the inverse of that. Or excuse me, the A is going to be the inverse of that. So we're going to take A inverse inverse, and that's going to equal the inverse of this whole thing. So A31, A32 negative 1, M3 1/5, A23 2, P A12 negative 1. Invert those, you get A12 negative 1 inverse, P23 inverse, A232 inverse, M3 1/5 inverse, A32 negative 1 inverse, and 1 inverse. Great, so that's A. So A is thus going to equal, and we'll rewrite this now, okay, a little bit of writing going on here. We're going to get A12 negative 1, so in fact, let's rewrite this whole thing first here. It's going to be A12 1, right, because the inverse of a permutation matrix is itself. A23 negative 2, M3 5, right, because you take the inverse of 1/5, A32 positive 1, A31 negative 1. And those are your elementary matrices that are going to make up A. So A is thus going to equal, and we'll now write these down. I've got in the slot 2, 1, I'm going to have a 1, so that's going to be 1 right there, 1, 0, 0. Here we go. P23 is going to switch the second and third columns. A23 is going to have in slot 3, 2, it's going to have a negative 2. So negative 2 here, 1's along the diagonal, 0's everywhere else. M3, 5, we're going to have 1's on the diagonal except a 5 here in the third row, 0's everywhere else. A3, 2, 1, in the slot 2, 3, so 2, 3, we're going to have a 1, 1's on the diagonal, 0's everywhere else. And then A3, 1, negative 1, we're going to have a negative 1 in A13, 1's on the diagonal, and 0's everywhere else. Multiply those all together, and you should end up with 1, 0, negative 1, 1, negative 2, 2, 0, 1, 1, which is the matrix that we started out with. So what I want to actually show and kind of, emphasize here is, first things first, elementary matrices, they are invertible. Okay, we can go in and we can find their inverses, and their inverses aren't so bad. They're actually pretty easy to figure out. There's a couple of rules, and those rules are actually mentioned earlier. Secondly, the set of elementary matrices that we used in order to row reduce A, that turns out to be A inverse. That's really handy. It's handy to know that that's going to give you A inverse. And then we utilize A inverse then to go out and find A. We take the inverse of those elementary matrices, and remember that not only are you taking the inverse of each individual matrix, but you've got to switch their order. You've got to run their order backwards in order to actually generate A, okay? And that's basically what we did here, all right? Hopefully this makes some sense. If you still need some work on your elementary matrices, going through and generating them, please go in and take a look at the video previously that's inside of the comments. This is Dr. George Sweeney, and I want to thank you for watching my video. If you found it helpful and you liked it, go ahead and click the thumbs up. If you want more of these videos and you want to get my updates, please click subscribe. If you have any questions or you just want to say how much you really enjoyed the video, go ahead and leave some comments. I do read and respond to the comments.